I often see people online use the phrase, "explain like I'm 5, when they want a simple explanation of a complicated topic. They might want an explanation of how planes can fly or how GPS works, explained in a simple way even a 5-year-old could understand. A little while ago, I came across a post that wanted an "explain like I'm 5" style explanation for mathematical objects called spinors. The post only got one response, and it started with, "I don't think spinors are something that can be explained like you're 5. Spinors are mathematical objects that come up in advanced quantum physics, and they have a reputation for being pretty confusing. If you've learned any particle physics, you might know that all fundamental particles can be broken up into two categories. The bosons, which, loosely speaking, are the force-carrying particles, and fermions, which are the matter-type particles that make up atoms. All known fundamental bosons have either spin 1, which are represented by vectors, or have spin 0, which are represented by scalars. Vectors and scalars are familiar mathematical objects to any undergraduate physics student. However, all known fundamental fermions have spin 1/2, and these are represented by spinors. So, around half of all known fundamental particles are described by spinors. But what exactly does that mean? A first introduction to spinors will normally explain them in terms of how they transform. Euclidean vectors are basically just pointed sticks, arrows, and when we turn them around 360 degrees, they end up back where they started. But when we turn spinors around 360 degrees, they come back to the negative version of themselves. It requires 2 full turns, or 720 degrees, to get a spinor back to where it started. The property of requiring 2 full turns to get back to the starting position is one of the defining properties of spinors, and this is demonstrated by Dirac's belt trick. If we turn the free end of this belt once, we get a twist that cannot be removed by translating the free end around. However, after a second turn, we can remove the twist by moving the free end like this. A similar trick can be done by holding a cup or a plate. One turn leaves your arm with a twist, and a second turn gets you back to where you started. Now, these are cute tricks, but when I started seriously learning the mathematics of spinors, I found most textbooks were incredibly hard to follow, and I was left confused and frustrated. I've spent over a year studying spinors, and at this point I think I have the basics down. My goal now is to make a video series that lays out the basics of spinors at a level appropriate for undergraduate students, or early graduate students, so that they don't have to waste as much time being confused like I did. Like most complicated topics, I think it's best to learn spinors in stages, as if you're climbing the stairs on a staircase, starting with the easiest and most basic explanation and gradually getting more complicated and abstract. My planned staircase has 5 steps. Basic examples of spinors in physics, viewing spinors as the square roots of vectors, viewing spinors as members of Clifford algebras, viewing spinors in terms of Lie groups and Lie algebras, and finally talking a bit about how spinors are used to describe all spin 1/2 particles in particle physics and quantum field theory. So for the rest of this video, I'm going to give an overview of the steps in this staircase. You probably won't understand a lot of what I'm going to say, but right now I'm just trying to give you a basic roadmap of the ideas that will come up later in this series. I'll dig into the details as the video series goes on. So a good place to start learning spinors are examples from physics, such as basic quantum spin states and the polarization of light waves. In introductory quantum mechanics, we learn that putting electrically neutral silver atoms through a magnetic field forces them to choose between one of 2 states, either spin up or spin down. In physical space, up and down point in opposite directions, 180 degrees apart. But the quantum spin up and spin down states of a particle don't live in physical space. Instead, they live in an abstract state space. The rules of quantum mechanics tell us that when two states are mutually exclusive, they must be orthogonal. The spin-up and spin-down states of a particle are mutually exclusive, and so they are orthogonal, separated by 90 degrees. So here, we see there's an angle doubling relationship between these two spaces. A 90-degree turn in the abstract state space corresponds to a 180-degree turn in physical space. This means that doing a full turn in the state space corresponds to 2 full turns in physical space. Requiring 2 full turns to get back to where we started is exactly what we would expect from spinors, and so matter particles are best described using spinors. We can write a spinor as a 2-component column, where the 2 components indicate the probabilities for measuring spin up or spin down from a given quantum state. Another example of spinors comes from classical physics, where light is described as a wave. The orientation of this wave is called its polarization. 2 basic types of polarization are vertical polarization and horizontal polarization. If we take a vertically polarized wave and rotate it 90 degrees, it becomes horizontally polarized. After another 90-degree rotation, it becomes vertically polarized again, although with its phase shifted by half a cycle. Again, we have an angle doubling relationship between physical space and the polarization state space. A half turn in physical space corresponds to a full turn in the polarization state space. While this is not the exact same as our example with quantum spin states, it does turn out that we can describe polarization states of light using spinors. Once again, we can write the spinor as a 2-component column, where the 2 components indicate the amounts of vertically and horizontally polarized waves inside a given light wave. It's worth noting that this is a purely classical effect with no quantum mechanics at all. Spinors are just mathematical objects, and while they are very important in quantum mechanics, they can be used to describe things in classical physics too. Now that we have some motivation from physics, the next step is to discuss spinors from a purely mathematical point of view. Here we learn that spinors are like the square roots of vectors. This means that we can take a 3D vector and use a special trick to factor it into a column spinor and a row spinor. With a matrix, which is a rank 2 tensor, we can sometimes factor the matrix into a column vector and a row vector, which are both rank 1 tensors. So we can factor a rank 2 tensor into a pair of rank 1 tensors. Now, if we have a vector in 3D space with components x, y, z, we can use a special trick to write it as a 2x2 matrix called a polyvector. This is done by multiplying each component of the vector by the sigma matrices. We can then factor this 2x2 polyvector into a column spinor and a row spinor, called polyspinors. So, loosely speaking, we're factoring a vector, which is a rank 1 tensor, into a pair of spinors, which are sort of like rank 1/2 tensors. Now, when we rotate a 3D vector, we usually use a 3x3 rotation matrix like this. But when we rewrite our 3D vector as a 2x2 polyvector, rotating the x, y, and z components is instead done with a pair of rotation matrices, one on each side. Each matrix is responsible for half of the rotation. If we then factor our polyvector into a pair of polyspinors, notice that each spinor only gets one rotation matrix. So each spinor only rotates half as much as the vector does, just like we saw with quantum spin states and polarization states of light. So when looking at all the different ranks of tensors, we can think of spinors as fitting in right here. A spinor is sort of like a tensor of rank 1/2, because we can combine 2 spinors into a rank 1 tensor, and because spinors transform half as much as vectors do. While polyspinors are associated with rotations in 3D space, In special relativity, it's also possible to get spinors associated with four-dimensional spacetime, which are called Weyl spinors. This is a bit confusing, as polyspinors and Weyl spinors are different kinds of objects, but they both look like two-component columns. We'll clear up the difference between them in future videos. The next step in the staircase is Clifford algebras. Clifford algebras are a bit abstract, but they help us define spinors in any dimension, not just 3 or 4 dimensions. Most physics students are familiar with scalars and vectors, but sometimes in physics it's more useful to use their higher dimensional analogs, bivectors, trivectors, and so on. For example, it's much more natural to represent angular momentum using a bivector, which is an oriented plane, instead of using a vector, which requires the awkward right-hand rule to make sense of. We can build these bivectors using the wedge product. The wedge product of vectors u and v is a plane formed by the vectors u and v with an orientation that follows the arrows. If we swap the order of the vectors, we get the same plane, but with the opposite orientation. These are called bivectors, and they're a much more straightforward way of representing rotations. With the wedge product, we can build bivectors, trivectors, and the other higher dimensional multivectors, which make it easier to represent geometric ideas in physics without having to rely on vectors for everything. An algebra with the wedge product is called a Grassmann algebra, or sometimes an exterior algebra. When an algebra has both a wedge product and a dot product, we call it a Clifford algebra, also called a geometric algebra. The Clifford product of two vectors is like a combination of the dot product and the wedge product. In the Clifford algebra for 3D space, the basis vectors are the sigmas we saw before. And in 4D spacetime, the basis vectors are the gammas. In Clifford algebras, vectors are also rotated using double-sided transformations, just as we saw with polyvectors. Spinors also arise naturally in Clifford algebras for free. Here we can see the spin-up and spin-down states from quantum mechanics represented in a Clifford algebra. We'll see that spinors can be defined as members of minimal left ideals in Clifford algebras. This is a pretty abstract sounding definition, but we'll approach it slowly over several videos, step by step. Ultimately, this is just a set of instructions for writing down spinors using the right combination of scalars, vectors, and bivectors, and it works in any dimension. Now, while being able to define spinors in any dimension is nice, when it comes to physics, the most important spinors are associated with three-dimensional space and four-dimensional space-time, the polyspinors and Weyl spinors. In particle physics, each type of particle has its own spin value, with all known fundamental particles being either spin 0, spin 1/2, or spin 1. Composite particles can have higher spin, like spin 3/2, and the theoretical graviton has spin 2. Any theory of quantum mechanics that incorporates relativity will require us to understand how different particle types transform under a change of reference frame. To understand this, we need to learn the theory of Lie groups and Lie algebras. If we exponentiate this 3×3 matrix here times theta, we get a rotation matrix in the xy plane. We say that this rotation matrix is part of the Lie group SO3, and this matrix we exponentiate is called a generator, and is part of the Lie algebra SO3. There are generators for all the 3×3 rotation matrices, and the generators follow special commutation relations, which is why they form a Lie algebra. If we use these commutation relations as a starting point, we can find many generator matrices of all different sizes that satisfy them. When we exponentiate these generators, we get rotation matrices for all the different particle spin types. The 3x3 matrices rotate the standard 3D vectors. The 2x2 matrices rotate polyspinors. And all the other matrices rotate particles with other spins. So looking at the different matrices that come out of this Lie algebra gives us a recipe for rotating particles with different spins in 3 dimensions. We can follow similar reasoning for Lorentz transformations in special relativity with the Lie group SO13, which has 6 generators. And this tells us how to transform Weyl spinors and particles of other spins according to Lorentz transformations. At this point, we'll have most of the math required for understanding spinors, so we'll look at how they are used in particle physics. Modern particle physics treats particles as excitations in various fields. For example, an electron is an excitation in the electron field, and a photon is an excitation in the photon field. The spin-0 Higgs field is a scalar field. The spin-1 force-carrying particles are each vector fields, and the various spin-1/2 matter particles each have spinor fields. The study of these fields is called quantum field theory, or QFT, and the interactions between these various fields are modeled by an enormous formula called the Standard Model Lagrangian. Any terms in this formula that contain a pair of fields represent an interaction between those fields. For example, this term represents the electron spinor field interacting with the photon vector field. Spinors in quantum field theory are 4-component columns called Dirac spinors, which are really a pair of 2-component Weyl spinors, one having left-handed chirality and the other having right-handed chirality. Ordinary tensors only have 2 index types, upper and lower. But because Weyl spinors come in both left-handed and right-handed versions, they require 4 index types, using dots for right-handed spinors and no dots for left-handed spinors. This notation is called the van der Waarden notation. One interesting fact is that the weak nuclear force is only known to interact with left-handed particles. So reflecting the universe in a mirror, or equivalently swapping the left and right-handed particles in the formula, does not result in the same physics. And studying quantum field theory will help us understand how the various forces, like the weak force, interact with the various spinor matter particles. The study of quantum field theory can last several semesters in graduate school, so in this series I'll only be scratching the surface of how spinors are used in it. So I realize if you've never studied spinors before, everything I just said was a lot to take in. You don't need to understand any of it now. I'm just trying to give you a basic roadmap for where this video series is going. I also don't expect everyone to finish every single video in the series. Some people might have their curiosity satisfied after the first couple steps and decide they don't need to watch anymore, and that's fine. But I'm hoping that anyone who wants to learn about spinors in any level of detail will find this video series helpful in untangling a rather confusing topic in physics. So if you're interested in watching more, I've left a link to the playlist in the description, and we'll start with learning some basic examples of how spinors are used in physics.